Hey everybody, this is Barnaby and Saya. Today we're teaching about mass percent and about moles. So mass percent is like you just did with your penny lab, where you found the percent of copper and zinc in a penny. So percent in general is the thing that you want the percent of divided by the whole amount times 100. And it's no different here for chemical formulas. You have a question?
Actually, instead I'm gonna go play outside.
Oh, okay.
Yeah.
So I was gonna go play outside. Okay, so for example, let's find the percent of hydrogen and the percent of oxygen in water. So we're going to do it by mass, and we have masses for each element on the periodic table. It's the number under each element. So hydrogen is 1.01 gram, that says on the periodic table, and there's two of those, so the total mass of hydrogen is 2 times 1.01. The whole compound is the two hydrogens plus one oxygen, which on the periodic table on the bottom says 16.00 grams. And then to turn it into percent from a decimal, we multiply by 100. We do this thing for oxygen, so it'd be the mass of just one oxygen divided by the mass of the whole thing times 100. So you get 11.2% hydrogen, 88.79% oxygen. I would recommend that you calculate each one instead of subtracting from 100 for one of them, because then you have a check of whether you did it right. So that's all there is to that. The general formula for calculating it is the grams of the element from the periodic table divided by the grams of the compound that you added from the periodic table times 100. Here's another application of percent composition. You can have the percent of a whole thing that's normally a compound in another formula. So when we were classifying matter, we saw a picture of copper 2 sulfate pentahydrate, a pretty blue crystal. A hydrate in general is a crystal. That means it's ionic. That means it has a metal and a non-metal that are ions that stick to each other because one's positive and one's negative. And it has the water actually integrated into its structure, bonded there. And so the amount of water in a particular hydrate is always set. It's a ratio. So you can find percent of water in there. So for example, you could say, what's the percent of water in aluminum sulfate trihydrate? So this looks like a kind of intimidating formula, but the dot is actually part of the formula. It does not have anything to do with math. It's just like an attachment, like how I said the waters were bonded in there in the crystal, in the spaces in the crystal. So we're just going to add everything up. We're not going to multiply when it says dot. And this would be a good time to pause the video and see if you can find the percent of water in the whole thing. You would do the mass of the water divided by the mass of the whole compound times 100. So here's how we would do it. The water, there's 3 of them. We added up in the previous problem. It was 2 hydrogens and oxygen is 18.02. And then the whole thing is the 2 aluminums plus 3 sulfurs. I'll come back to the subscripts. Plus 12 oxygens. Plus the 3 waters, because that's part of the compound also. Okay, so let me look at the subscripts again. I highlighted the plus because you don't multiply. The dot in the formula does not mean multiply. It means that there's attachment there, a bond there. It's just part of the notation for writing chemicals that are hydrates. Okay, so if a subscript only modifies what it's immediately next to its left. So the 2 is only for aluminum. The 4 is only for the oxygen. The 3 is only for everything in the parentheses. That means there's 3 of the 4 oxygens, that's 12, and there's 3 of the 1 sulfur, so that's 3. Students often get confused on that when they're first starting out, so that's another good thing to pause the video and do the subscripts make sense for how many of each thing there are. And then when there's a coefficient, which we'll use in balancing, or we used in balancing earlier today, the coefficient affects everything after it. So there's 3 of the 2 hydrogens, so that's a total of 6, not 5. Sometimes students add them up, where the 3 is saying there's 3 waters, so there's 3 twos, so there's 6. Okay, so you wind up with 13.64% water. Here's an application of the percents. So let's say we have 10 grams of 2 compounds, and we know their formulas, and they're going to burn. They're going to combust, like we talked about in class, reacting with oxygen, which creates more CO2. So when we think about this, we're like, oh, the oxygen's coming from the air, the carbon has to come from these compounds. So whichever one has more carbon is going to make more CO2. So since we know how to do percents, we can look at these, and whichever one has a greater percent of carbon, since they're both 10 grams, they'll have a greater amount of grams that can then become CO2. So we don't actually have to calculate all the way. We can just kind of estimate. We can say, oh, well, grams of carbon in CH4, that would be 12 grams of carbon. 12.01 is the number on the periodic table. And the whole thing would be adding 4 1.01s to that, so over 16. Okay, so that's about 75%. The C3H8 is going to have 3 carbons in it, so that's 36.03. And then plus 8.08 for the hydrogens, so 44 total. And I don't even have to calculate that. I can see it's more than 44%. More than 75%. If it was 75%, it would be 33 out of 44, I think is how you do it. So because it's more than 75%, that has a greater percent of carbon, so it has a greater mass of carbon, so it'll make a greater mass of CO2. You might be noticing that these videos go pretty fast because I actually wrote in advance and I'm just recording over it. That's so that if by watching it and maybe putting out these notes from Neo, you understand it, you don't need to go back to it more, it makes sense in your brain, you can figure it out yourself, that you're done, because I know you have a lot of stuff to do, but realize that this is a lot faster than we would go if we were in person in class. So if you need to pause after each problem and write stuff down and try it yourself and post to the forum if you have any questions, please do. So we were just talking about percent of masses, and I said, well, we have these masses on the periodic table that you can use to compare atoms to each other to find percents. Here's a little bit about where that came from. This won't be the experiments that people did to find relative atomic masses won't be tested directly. So it turns out that you can put a gas on a scale and you can weigh it. It's actually a little bit tricky. Sometimes you need to, it's tricky because the thing you're weighing is in kind of a sea of air, almost as if it were a fluid. And so there's buoyancy, and weighing something that's very light when it's buoyant might be hard. But anyway, basically you put some gas on a scale, like let's say hydrogen, and you might get a mass of 2. And you can put something else on the scale if it's the same pressure and same volume and same temperature of gas, and then you can compare those masses. When gases have the same pressure and volume and temperature, then they have the same number of particles in their atoms or molecules. So you can compare the weights and say the same amount of each gas weighs this much. So helium is twice as heavy as the same number of particles of hydrogen, for example. And if you look on the periodic table, you can see that's true. Notice hydrogen comes as H2, like we were talking about with the diatomic elements. So you can also do that with compounds. And that's another way to find the masses of elements. If you were measuring, let's say, a chemical that both had the same of one element, like 4 hydrogens each, but a different number of carbons, then you could compare the masses and find the difference, and that would be that element. So like here we have CH4 is 16 and C2H4 is 28. So then that C then must be 12. So these numbers I made the same as on the periodic table on purpose, so you could see how they correlate. These numbers are in grams. That's called the molar mass. It's for a mole of chemical. A mole comes from a word that means pile of stuff, so a little pile of stuff. When you measure individual atoms, those masses on the periodic table also work, but then it's in units called atomic mass units, so that's pretty convenient. So here's some pictures of moles. So here is the masses are close to the masses on the periodic table for these elements. You can see it's a little pile of things that would fit on a filter paper. These little papers that the chemicals are on are probably about 4 inches in diameter. So these are pretty small amounts of chemical. It's a little pile of stuff. That's how much a mole is. You can see that a mole is a certain number of atoms. It's 6.022 times 10 to the 23rd atoms. I think on your equation sheet that you get to use for AP Chemistry that I need to give you, it's 6.02 times 10 to the 23rd. That's fine too. I tend to do 6.022 because then it helps me remember the exponent is one more than that, times 10 to the 23rd. So these are the same number of atoms of all of these, just like I showed you with the gases. You can find which samples have the same number of particles. And the number of particles in a mole came from just taking the lightest thing that anybody had weighed accurately, which was a hydrogen atom, and dividing it into 1. So you divide 1 by a very small number and you get a very big number. Because they needed a big number to be able to work with a manageable amount of chemicals and know how many atoms there were. So these are the same number of atoms of each chemical. It's 1 mole, it's 6.022 times 10 to the 23rd atoms, but you can see that they're different masses because atoms weigh different amounts. They're different volumes because atoms have different structures and different volumes. But since they're the same number, they allow us to calculate how much of a element do we need to measure in order to make a certain amount of product, kind of like cooking. So in a science lab, we would weigh an amount, and then we would want to know how does that amount compare to whatever it needs to react with. So we know what amount we're going to get or how much of the other reactant, how much of the other ingredient we need. So we convert to moles for that. Here's how we can convert to moles and to atoms. You can convert from grams to moles using the molar masses on the periodic table on the bottom of each element. Those are the masses per 1 mole. So if we were going from grams to moles, we would be multiplying by conversion fraction with grams on the bottom. That comes from the periodic table, moles on the top. That's 1 because molar mass is defined to be from 1 mole. So I'm looking at this fraction here. If we are going the other way from moles to grams, then we would be putting moles on the bottom to cancel out and grams on the top, and grams you find on the periodic table. From moles to atoms, we have a definition because somebody made that up. They said, well, let's define 1 mole, 1 pile of stuff, to be equal to 6.02 times 10 to the 23rd atoms. So if we're going from moles to atoms, then we would put moles on the bottom of the fraction we're multiplying by to cancel out, atoms on the top. The number that goes with atoms is 6.02 times 10 to the 23rd. The number that goes with mole is 1 because that's defined to be that many atoms for 1 mole. And you can also go the other way, but then the fraction flips. So remember, using conversion fractions, start with number in the problem, multiply by fraction, put the unit you want to cancel out on the bottom and the unit you want on top before you fill in any numbers so you don't accidentally flip the fraction, and that gives you an opportunity to think about what numbers you need. So for example, we could say how many atoms and 10.13 grams of copper. So from grams, we'll start with the number given to us in the problem. We're going to convert to moles and then convert to atoms. It's certainly possible to do just one step with the right units, but I'm going to always show 2 steps because in other problems we'll go just from grams to moles or just from moles to atoms. So I'd like you to be familiar with all the steps and not try to skip. Okay, so start with the number given to you in the problem. Multiply by fraction line. Unit that you start with goes on the bottom to cancel out. Unit that you want, which is moles, goes on the top. And then you can ask yourself which is bigger, like we did before if you want. A mole is bigger. 1 mole of every element is more than 1 gram. So a mole is bigger, and there's 1 mole. And then where do you find the number that goes with grams on the periodic table? So you fill that in. Please use all the digits that the periodic table gives you that I linked in your agenda. Okay, so if the problem asks for moles, you would stop there and say 10.13 times 1 divide 63.55. This problem asks for atoms, so we have one more step. So multiply by fraction line. This unit's canceled out, so then the unit that's on top goes on the bottom to cancel out. The unit that we want goes on the top. Moles are definitely way bigger than an atom. In 1 mole, there's 6.022 times 10 to the 23rd atoms. So then check that all your units cancel out except for the one you're looking for. And you would say 10.13 times 1 times 6.022 exponent key 23 divide 63.55 divide 1. I would encourage you to use the exponent key, which is usually says EE, instead of times 10 to the 23rd, because if this number is on the bottom of a fraction, if that number is on the bottom of a fraction and you type 6.022 times, then instead of dividing, it'll multiply again unless you use parentheses. So I would use the exponent key. The way you use the exponent key is you just type 6.022 exponent 23. You leave out the 10 part. The exponent key means times 10. So Saya, you have any questions, Saya?
Well, anyway, what does that mean? And also, you put 17 minutes and 54 seconds.
It keeps going up. That is a long time. He says, what does this mean? This is how you do math to calculate how many atoms are in a pile of stuff.
But what I mean is only that blue top.
Did I cross stuff out?
What?
Where I cross stuff out?
Yeah, and that.
Yeah, that's the question. And then this is checking to make sure all your units cancel out except for what you want. If they do, then you did the problem right, probably. If they don't, then you definitely did something wrong. So it's a good check. Here's another example for you. Let's convert 44.01 grams of CO2 to molecules. So notice this isn't an atom, this is a compound, CO2. And so that's why it doesn't ask for atoms, it asks for molecules. You could find, after you have molecules of CO2, you could find atoms after that by multiplying by 3 if you want, since there's 3 atoms in this molecule, 1 carbon and 2 oxygens. So you start with the number given to you in the problem. Notice I'm saying all the steps for you, and I'm trying to say the steps the same every time. All these problems are the same, at least as far as they use the same steps. That's what's hard in chemistry, is the procedures. Once you know the procedure, then problems that seem different are actually pretty much the same. So start with the number given to you in the problem. Grams go on the bottom to cancel out. Always convert to or from moles when you're doing problems like this. Let's see, I should be pointing up here. Always convert to or from moles when you're doing problems like this. I call this graphic organizer of how to convert grams to moles to atoms and vice versa the mole highway. Like everywhere you go on the highway, left or right, you have to run over the mole. Moles go on the top. Moles are bigger, so that gets the 1. You find grams on the periodic table. So since there's a C and an O and an O, just like we did when we were doing percents, we need to add up the C and the O and the O. So that'll be 44.01 grams, that's 12.01 for carbon, plus 16.00 for oxygen, plus 16.00 for oxygen. And then convert to molecules. So molecules, I guess we'll do moles first. Moles go on the bottom to cancel out. Molecules go on the top to give us what we want. Notice you can abbreviate moles with MOL if you want. You can save writing that E, so that's a lot of time saved. Just kidding. Molecules, you cannot abbreviate MOL or MOLE because those are both for moles. Okay, so which is bigger, a mole or a molecule? A mole is way bigger. How many molecules in a mole? That's the definition of a mole. 1 mole of anything. Atoms, molecules, eggs would be a funny example. You could have a mole of moles, like the animal. There's interesting work with that on the internet, like a mole of moles would cover the surface of the moon to 4 miles deep or something, and then there would be so much weight on them that the ones at the bottom would start doing fusion or nuclear fusion or something, or I don't know, I might be saying it wrong. You can look it up if you're interested in funny things like that. Okay, so 1 mole of anything is 6.022 times 10 to the 23rd. Okay, so on your calculator you would do 44.01 times 1 times 6.022 exponent 23, divide 44.01, divide 1. Even though it's a 1, I'm saying divide to emphasize that you press divide before each thing on the bottom. So make sure all units cancel out, and you get 6.022 times 10 to the 23rd molecules of CO2. If you were going to try to find atoms, you would multiply by one more fraction. Isaiah? You would say times, and then times fraction. On the bottom, you would put molecules to cancel out. On the top, you would put atoms. And on the bottom, you would put a 1 because molecules are bigger than atoms. And on top, you would put 3 because 1 molecule of CO2 has 3 atoms. I'm not going to do this problem today. This video is already long enough, and I have a guess of how long it'll take you to do a good job writing down and thinking about this and studying. This is a lot, I know it. So I wanted to show you just how moles are useful in a problem like where it says a sample of C2H6 contains 10 grams of carbon. What's the mass of the whole compound? The information you have is the 10 grams and the formula. This formula is not by mass. It's not saying there's, let's say, 8 times as much mass of the whole formula as there is carbon. It's by number. There's 2 carbons and 6 hydrogens in the whole formula. So we can't compare masses like that because different atoms weigh different amounts because they have different numbers of protons and neutrons and electrons, but electrons weigh hardly anything. So we need to convert to something we can count, which is a number of atoms, which is moles. So once we convert the 10 grams to moles, then we can do ratios with the numbers in the formula to find the answer. Okay, if you need help, please post on the forum, help each other, text me, email me, and in class tomorrow we'll practice with all this. We'll probably do this example right here as our starter. Okay, thanks everybody.